Aparna Konar, and I'm a graduate student at San Jose State University. Today I'm going to present my project on a pipeline Mips architecture for Nios 2. I completed this project under the guidance of my professor, Dr. Chang Chu. Now, coming to the introduction of a Nios 2 processor. According to the Gartner research report recently, Nios 2 has been declared to be the most versatile processor for embedded systems. It is a 32-bit processor, embedded processor architecture basically, which has a reduced instruction set computer architecture. And this is a representation of the Nios 2 processor where you can see the optional FIFO memory and other logic. Takes the input as 32 bits. Data is moved between memory and these registers by means of load and store instructions. Now, the basic processor architecture, whenever we talk about the processor architecture, there are two names that come to our mind. One is the RISC and the other is the CISC. RISC is nothing but the reduced instruction computer architecture, which uses a reduced instruction set and can be implemented in a single clock cycle. For CISC, it's a complex instruction computer architecture and it includes multiple clock cycles. RISC is a register to register architecture. There are separate instructions for load and store instructions. For CIS, it's a memory to memory architecture and the load and store is incorporated in some different kind of instruction. Now there's a trade-off. Larger the code size for RISC, we have the advantage that the number of cycles per second is low. For CISC again, the code size although is smaller, but then number of cycles per second is very high. RISC spends more transistors on memory registers and CISC spends more transistors on storing the complex instructions. What is basically an instruction set? It is nothing but a boundary between the software and the hardware components. Most of the processors these days are using the RISC architectures. MIPS. MIPS was one of the first RISC architecture that was started about 20 years ago by John Hennessy, whose book we love to read and follow. It allows a parallel execution, it has minimized memory access time, and it is similar to most of the processor designs today, like Sun SPARC, IBM, Motorola, PowerPC, and ARM-based processors. Coming to the design principles of MIPS, MIPS has a very simple design architecture because it uses a fixed size instruction of 32 bits. The operational code is fixed to 6 bits, it will never exceed that. It uses a limited number of instructions so it is faster to execute. And being a good design, it has its own trade-off that it has just 3 instruction formats. So let us explain the 3 instruction formats. First we come to the I-type instruction. The first two A and B are 5 bits each. They are used as a general purpose register. Here the 16-bit field immediate provides immediate data which can be extended to 32 bits. And this opcode tells us the kind of operation that has to be performed. Example, add I, or I, sub I. The J-type instruction. In the J-type instruction is basically used for subroutine calls, stack operations and stuff like that. Here the 26-bit immediate contains unsigned immediate value. The format is used again to call, like jump to this particular register or jump and link. What kind of operation that is specified by the opcode. We then have the R-type instruction. Now R-type instruction here again, A, B, C here are 5 bits each. A, B can be used as a source and C as a destination general purpose register. This opcode tells us a kind of function that has to be performed, add, sub, mul, or the arithmetic operation that needs to be performed here. Coming to the idea of pipeline implementation. Basically, why do we need the pipeline? Goal here is to make the CPI less than equal to 1. How do we do that? We break the instruction into a number of stages. Each stage is nothing but a block of combinational logic. Latency of each stage fits within 1 clock cycle. We can insert registers between each pipeline stage to hold the intermediate values. Thus, we achieve 100% hardware utilization. Now, this will also allow us to execute each of the steps in parallel for a sequence of instruction. And thus, we achieve the pipeline that has been achieved here as well in this project. Coming to different stages of pipeline, how do we do it? We have the instruction fetch stage here. This is the instruction memory. This is the program counter. PC keeps a record of the next instruction. So this basically is responsible for the instruction. The IFID register here keeps a record of the instruction signals. And now then we have the decode stage, which is responsible for reading the contents of the register, the sign values and stuff. So this particular IDEX register has a record of the instructions previously, as well as it generates the control signals that is provided to the execute stage rather, to carry out the destined operation. The EX and memory cycle consists the results of the value as well as the controls that are generated for the next stage. Memory access stage generally deals with memory operations like fetching and loading to and from the memory. This contains the control signals of the previous stage as well as the signals for this mux, which tells it whether to write back the data to the register or to the memory and vice versa. The design models in my project are stage 1 consists of a PC module. The PC module is responsible for generating the next instruction. Adder PC here, what it does is that the next instruction PC is equal to the old PC plus 4, which is done here in the adder. The 32-bit mux selects one of the inputs depending upon the control signal. Instruction memory stores all instructions which are to be executed. In stage 2, I have a register file which contains 32 registers of 32-bit size, and R0 is always 0 irrespective whether you write or read from it. The control unit takes opcode and the opex or the function as its inputs and produces the control signals. One of the control signals is added to add capability of the stalls to the processor. Jump address is irrelevant for this particular project, but then if we need to calculate the jump address, then this can be done here in this module. Sign immediate block is used to extend 16-bit data to the 32-bit data. You have a stage 3 where this is stage 3 is the execution stage where you have the ALU, the adder and the branch select. ALU is the only module which is responsible for the manipulation of data here. Adder just adds the two 32-bit input and gives us a 30-bit output. The branch select here is used to produce a control signal select between the branch address and the normal PC plus 4. Then you have a stage 4. The stage 4 consists of a data memory and a mux. The data memory is nothing but the on-chip memory to store the data. The mux here is added to select either data memory output or the ALU operation depending upon the instruction. Stage 5 is nothing but the register write back stage. Selects the right data and then writes it to the register. And adding pipes means this stage converts a single cycle data path to the 5-stage pipeline architecture. How the instruction is fetched, here you can see it's fetched from the instruction memory, PC is updated with the current address, and here it is updated again. Decoding instruction, from the opcode field bits, the control unit comes to know what kind of operation it has to take. It reads the contents of registers on which the operation has to be performed, and the address of these registers comes from the instruction. Control unit, here as told earlier, from the decode stage it gets the opcodes and stuff, and then it generates the control signals to invoke the ALU. Load and store instructions. Now it gets the instruction from here, extends it, ALU gives us the address where the data is stored. Depending upon that, the write and memory read, the particular operation of the respective operation is performed. Branch instruction. Here we have the comparison between the registers, because here we are executing branch less than, so we need to know both the registers. So we read the registers here, we sign extended, compute the branch target address. Design aim was to calculate the dot product of two vectors. Here are the two vectors and we have to find the dot product. So now the code has been implemented and executed, and the waveforms that I achieved was here add I. As you can see, here the instruction is being fetched. Here it's being decoded. Since it's an arithmetic operation, we don't need the memory cycle. So here you see the sign extension executed and then we write it back. Add instruction, again it's fetched, decoded and executed. There's no memory operation and there we get the result. For branch, here we have two branch stalls and then the branch happens. For mul, here we have the instruction, decode and execute. Here we carry forward the result and write it back to register 8. For load, since there is a dependency, as you can see, R4 will not be available before the write back stage of the previous instruction. So we have two stalls for dependency. Data is finally available and we write it back. We finally get the result. 580 is the result which we write back to the register. That's the end of the project. So to complete this project properly, these are the things which are referred to. A Nios reference manual. Manuscripts of Dr. Changchu, my professor. The book by Hennessy and Patterson and some of the IEEE papers from the year 2011 to 2015. Thank you so much for watching my presentation patiently.